Chapter 12, Elementary Chemical Kinetics, Section 12.5, the Arrhenius Equation and the Eyring Equation. The Arrhenius Equation is an empirical equation proposed by Arrhenius. This equation describes the relation between the reaction rate constant K and temperature T. Although K is called the reaction rate constant, it's not really a constant. K does depend on temperature. As temperature changes, the rate constant changes. Arrhenius proposed that K is equal to A times e to the power of negative activation energy over RT. A is the pre-exponential factor. And then we have exponential function e to the power of negative E sub A over RT, where E sub A is the activation energy. There is also a modified Arrhenius equation. K is A times T to the power of M and times e to the power of negative E prime over RT. It contains one more parameter than the original Arrhenius equation. And usually when we have more parameters in the equation, well, we can use that equation to match with experimental data more accurately. The Eyring equation is another equation for computing the reaction rate constant K at different temperatures. The Eyring equation is the exact equation of K for first order reactions, assuming the quantum tunneling effect is negligible. We'll talk about quantum tunneling effect in quantum chemistry. So basically, without any quantum tunneling effect for a first order reaction, we can write out the expression for the reaction rate constant K. It's kBT over H times e to the power of negative. Over here we have Gibbs energy of activation over RT. Kb is the Boltzmann constant, H is the Planck constant. And the Gibbs energy of activation is denoted by delta G, double dagger. It's the Gibbs energy of the transition state minus the Gibbs energy of the reactant. At any given temperature T, delta G is delta H minus T delta S. Therefore, the Gibbs energy of activation is equal to the enthalpy of activation minus temperature times the entropy of activation. And therefore, we can rewrite the Eyring equation to a function of entropy times a function of enthalpy times, well, a constant. So really, we are just rewriting this delta G double dagger to delta H double dagger minus T delta S double dagger. We have two separate exponential functions. One is e to the power of entropy of activation over R. The other is e to the power of negative enthalpy of activation over RT. The enthalpy and entropy of activation both depend on the reaction temperature, but that temperature dependence is often negligible, it's often small, and often neglected. Now let's look at these two equations again. The Arrhenius equation, K is A times e to the power of negative activation energy over RT. Eyring equation, K is kBT over H times e to the power of negative, well, Gibbs energy of activation over RT. From the Arrhenius equation, we know Ln(K) is Ln(A) minus activation energy over RT. If we assume the activation energy is independent of temperature, it's a reasonable assumption, and then we have the first derivative of Ln(K) with respect to temperature is simply Ea, the activation energy over RT squared. Now let's look at the Eyring equation. We take the logarithm of K. Ln(K) is Ln Kb over H plus Ln T minus, well, this is the Gibbs energy of activation over RT. And because Gibbs energy and the change in Gibbs energy heavily depends on temperature, we want to make sure to separate G. G should be H minus Ts. Delta G in this case is delta H minus T delta S. So we have this equation over here. This Ln T comes from kBT over H. And over here we have negative enthalpy of activation over RT and plus entropy of activation over R. Now let's assume the enthalpy of activation and the entropy of activation are both independent of temperature. We can take the first derivative of Ln(k) with respect to temperature. We get 1 over T, it comes from Ln(t) and then minus 1 over R. And then over here, this is the first derivative of this guy. Alright, delta H over T, and then we have 1 over T plus the enthalpy of activation over RT squared. Now let's look at this from Eyring equation. d Ln(k) over dt is EA over RT squared. Let's look at this equation from the Eyring equation. d Ln(k) over dt is 1 over T plus the enthalpy of activation over RT squared. So we have these two equations side by side. They are both how Ln(k) depends on T, so I'm going to put an equal sign in between. So the activation energy over RT squared is approximately 1 over T plus the enthalpy of activation over RT squared. Therefore, we proved the activation energy is equal to RT plus the enthalpy of activation. We do have approximate sign here because the Arrhenius equation is not exact. So this is a approximate equation for computing rate constant K. And E sub A, well, may slightly depend on temperature. And also, when we take the first derivative over here and over here, we are assuming this enthalpy of activation and entropy of activation are completely independent of temperature. So we did make approximations. We want to emphasize the approximation by using this approximate sign. Again, the activation energy is approximately the enthalpy of activation plus RT. Again, we assumed this enthalpy of activation and entropy of activation are both independent of temperature. Well, this is just because the isobaric heat capacity of the transition state is often very close to the isobaric heat capacity of the reactants. We can write out the temperature dependence of the enthalpy of activation and also for entropy of activation. You can see this enthalpy of activation at T2 is equal to enthalpy of activation at T1 plus this integral of delta CPM dt. And this integral is often smaller than this item or this item. Therefore, we often say, well, the enthalpy of activation is approximately independent of temperature. What about entropy of activation? Well, the entropy of activation at T2 equals the entropy of activation at T1 plus the integral of delta CPM dt over T. And again, this integral is typically smaller than this item or this item. So approximately we say the entropy of activation is approximately independent of temperature as well. Now, what is this delta CPM with a double dagger in the superscript? It's simply the CPM of the transition state minus the CPM of the reactant. Delta CPM is often in the order of 10 to the power 1 joule per mole Kelvin. And if you integrate this over a narrow or moderate temperature range, well, the integral of delta CPM is, I think, roughly in the order of 0.1 kilojoule per mole. While delta H is often tens or even hundreds of kilojoule per mole. That's why this integral is negligible. And over here, if you look at again a small temperature range, and then you look at the value of this integral, it's often in the order of 10 to the power 0 joule per mole per Kelvin. And that's usually much smaller than the entropy of activation. And therefore, we often neglect this integral and assume the entropy of activation is also independent of temperature. Previously, we said the activation energy is equal to the enthalpy of activation plus RT. But if we assume both EA and delta H are independent of temperature, why the difference between these two depends on temperature? Again, if you look at this, the activation energy minus the enthalpy of activation is approximately RT. So that's dependent on temperature. But we did assume the activation energy is independent of temperature. We assumed enthalpy of activation is independent of temperature. But now the difference depends on temperature. Why is that? Well, again, it's just because the Arrhenius equation is inexact. E sub A might slightly depend on temperature as well. And also delta H and delta S do depend on temperature. It's just the dependence is small. However, when we derive, d ln k over dt, we completely neglected the temperature dependence of the enthalpy and entropy of activation. Now, even if we have this equation, sometimes we say delta H of activation is roughly the activation energy. Why is that? Because RT is often much smaller than the activation energy and also much smaller than enthalpy of activation. So we can also approximately say the activation energy equals the enthalpy of activation. It's reasonably accurate at low temperature. For example, RT is only 2.5 kJ per mole at room temperature. RT is only 3.3 kJ per mole at 400 Kelvin. And the activation energy, the enthalpy of activation of most reactions are typically in the order of tens of kilojoule per mole. So that means, well, this RT is usually much smaller than delta H. This RT is usually much smaller than E sub A, and therefore approximately E sub A is equal to the enthalpy of activation. Again, from the Eyring equation, we can take the logarithm of K. Ln K is Ln kBT plus Ln T minus the Gibbs energy of activation over RT. And we do need to separate this delta G into delta H and T delta S in this manner. Note that we have over here T delta S on top and RT on the bottom, so T and T cancel. And now we can actually move this Ln T to the left hand side. So Ln K over T is a linear function of 1 over T. The slope is negative enthalpy of activation over R. The intercept is Ln kB over H plus the entropy of activation over R. If we assume delta H and delta S are independent of temperature, then this graph is linear. We can plot Ln K over T versus 1 over T, get the intercept, get the slope, and then we can determine the enthalpy and entropy of activation. Again, the slope is negative enthalpy of activation over R. The intercept is the natural logarithm of kB over H plus the entropy of activation over R. So again, if you just generate a plot of Ln K over T versus 1 over T, we can get the slope and intercept simultaneously and then determine the enthalpy and entropy of activation quickly. From the Arrhenius equation, we have Ln K equals Ln A minus the activation energy over RT. A is the pre-exponential factor. And we usually assume this A is independent of temperature, and then the slope of Ln K versus 1 over T is negative activation energy over R. The intercept of Ln K versus 1 over T is the natural logarithm of the pre-exponential factor A. So this way we can compute the activation energy and the pre-exponential factor given the plot of Ln K versus 1 over T. So now let's compare this two side by side. Given the Eyring equation, we need to make a plot of Ln K over T versus 1 over T. For the Arrhenius equation, we need to generate a plot of Ln K versus 1 over T. The vertical axis is different. We have Ln K over T here, and we have Ln K directly from the Arrhenius equation. Now let's look at one numerical example, problem 12.5.1. Let's determine the activation energy and the enthalpy of activation for an elementary reaction from A to P with a reaction rate constant of 0.02 per second at 400 Kelvin and 2 per second at 500 Kelvin. And you can see as the temperature goes up from 400 to 500 Kelvin, the rate constant increases from 0.02 to 2 per second. That's a big increase by a factor of 100. Now let's look at the slope of ln k over t versus 1 over t. The slope is negative delta H over R. This delta H with double dagger is the enthalpy of activation. So we can either make a graph or we can do this calculation by hand. So the slope is simply, remember, delta y over delta x if you're looking at the slope of y versus x. So really it's the change of the vertical axis divided by the change of the horizontal axis. The vertical axis is ln k over t. The horizontal axis is 1 over t. We do this calculation, we get the slope negative 8,764 Kelvin. We compute the enthalpy of activation to be 72.9 kilojoule per mole. Now we're going to do the analysis assuming the Arrhenius equation can be used for this reaction, and then we plot ln k versus 1 over t. The slope is now negative activation energy over R. Again, the slope is just delta y over delta x, with y as the vertical, x is the horizontal. So delta y is just the difference between the ln k values, and delta x is the difference between 1 over t values. We get negative 9,210 Kelvin. We calculated this activation energy to be negative R multiplied by the slope. It's 76.6 kilojoule per mole. You can see the activation energy and the enthalpy of activation are really close to each other, 72.9, 76.6, but they do differ. If you take the difference between these two, it's actually roughly RT. So if you do activation energy minus the enthalpy of activation over R, you get 446 Kelvin. And let's look at the temperatures. It's 400 Kelvin, it's 500 Kelvin. So the difference between activation energy and the enthalpy of that activation is roughly, well, a temperature between 400 Kelvin and 500 Kelvin. Again, we verify this equation numerically. The activation energy is approximately equal to RT plus the enthalpy of activation.